Hey guys, welcome to another day of physical science. Today we're going to talk about something called phase changes. So, earlier over the course of the year, we talked a little bit about what a phase change was. You've got three phases. Well, you've got four. Three that we're going to focus on in this class: solid, liquid, and gas. The other phase, for those of you worried, is plasma, which is like a superheated gas. But solid, liquid, gas are the main three. And a phase change is if you start at one phase and then you go to another one. So, for example, you could start at a solid, go to a liquid, or a liquid and go to a gas. So, right here are the 6 different phase changes that we'll expect you to know. My guess is you've already heard of 4 of them. My guess is you know what melting, boiling is. My guess is you probably know what freezing and condensation are. Sublimation and deposition might be the two that look a little bit different from you or for you, but I bet you can kind of guess what they are just by kind of thinking what other phase changes are there. Okay, so here we go. Melting is solid to a liquid, boiling is liquid to a gas, condensation is gas to a liquid. Sublimation is when you go directly from a solid to a gas. Freezing is when you go from a liquid to a solid. And deposition is the opposite of sublimation, when you go from a gas directly to a liquid. So it kind of deposits solid out of the gas. That's how I like to think about it. And subliming looks very spooky. And when they say something sublime, they mean like otherworldly, spooky, I think. I don't know. Anyways, that's how I remember them. Yeah, here's a little picture showing you all the different physical changes. So here we've got a picture of solid things. Notice how closely they are together. Liquid things are a little bit further apart. And then gaseous things, a lot of space here in between them. And then so melting is when you go from solid to a liquid. Boiling is when you go from a liquid to a gas. And sublimation, you kind of skip that liquid phase. You go from a solid directly to a gas. And then kind of the other way here for condensation, gas back down to a liquid. Freezing is liquid to solid. And then going from a gas directly to a solid, that's number 6, that's deposition. Great. Make sure that you have what's in words over here written down in your notebook. You're definitely going to want that. This picture I found is helpful. I don't know, maybe it's not for you. That's up to you to make a decision on that. But definitely have these words over here. The whole melting is solid to a liquid, boiling is liquid to a gas. Just write the ones you need to know. Okay, I'm going to stop talking. We're going to move on to the next slide. Cool. So you might have seen this slide before. Pretty much what we're here to tell you is that solids are very close together and they're very slow in terms of the particles. So for example, here, all 3 of these particles are H2O. So the red ball is an oxygen atom or an O, and then the 2 white balls to the side of that oxygen atom are hydrogen atoms. So that's where we get the 2 H's and the 1 O from H2O. So what these words are trying to tell you here is that solids are very, very close to each other in terms of their particles. And then we see that with the actual like shape of a solid. Right? A solid has a fixed shape. You can't really like move it or anything like that. Solids also have a fixed volume. If you take a solid like my phone over here and you compress it, it's going to stay the same size. Even if I was to like break my phone in half, I'm not going to do that because I'm not an idiot. But if I was to like break my phone in half, it would still be the same volume. There's no way I can really like scrunch up that solid any tighter than otherwise. And then particles move slowly is kind of the reason why it has a fixed shape and a fixed volume. Because the particles are super close to each other, they can't really be compressed anymore. Liquids don't have a fixed shape. That's true. If I were to take this bottle of water and just pour it on the ground, instead of looking like a bottle of water, it would look like a puddle. So liquids don't have any sort of fixed shape, but they do have a fixed volume. You can't compress a liquid. Let's say you maybe have a liter of water. You can't squeeze that liter of water into half a liter size. But you could do that with a gas. So let's talk about gases here. Gases have no fixed shape and they also have no fixed volume, which is to say that if you blow up a balloon, you could actually shrink that balloon size by like cooling it off. or by just like squeezing it. You can see this most easily with like a syringe. Okay, so let's actually show you what happens with this syringe over here, which is filled with water, and this syringe over here, which is just filled with gas. Let's take a look at the gas syringe first. So in a gas syringe, we say it has no fixed shape, no fixed volume. So right now, if you look at it, the volume's at about, I don't know, 20-ish, somewhere around there. And what you'll notice is I can actually compress this thing pretty far, right? Which is just because I'm super strong. And then you might have been able to hear that it kind of lets out a little bit of gas as you compress it. So here it's all the way full, and now I'm compressing it, and it releases a little bit of gas. Over here, however, I've got this guy, which is actually, I don't know if you can tell this, but it's filled with water. So now what I'm going to try and do is try and compress it. And it doesn't matter how hard I push this, it doesn't compress. So, and when I let it go, it's going to actually shoot a little bit of water out. So, oh, you couldn't see that, but I just squirted water across the classroom. It's really fun. So yeah, the idea here is that liquids have a fixed volume, but gases do not have a fixed volume. So in both cases, I had the same amount of water and gas to start with. This is a fixed amount of gas that's in here. No gas is escaping, but I can still compress it. So what that means is the gas that I actually have in here can change its volume. If I let go of the plunger, notice how the gas returns to kind of its original volume. Kind of cool. Okay, so the other thing I wanted to talk about is the phase change graph of water. Just to kind of show you some interesting things actually about what happens when chemicals undergo phase changes. So this is true for water. It's also true for any other chemical that you're working with. So here is our graph. Whoa, bam, there it is. On our x-axis, we're going to have time. So we're going to look at, imagine like we're going to start with an ice cube and then we're going to heat it up. And what we'll look on the y-axis then is temperature. So we're going to start with an ice cube at -40 degrees Celsius, and then we'll take a measurement at 0, and then at 100 is also an important part. Question I have for you is, why is 100 degrees Celsius, why is 0 degrees Celsius, why are those two numbers important? Think about it. What do you think? Is it maybe because it's well, anyways. Okay, so here's what the graph looks like. You have a line kind of from -40 to 0. So as you're heating up the ice cube over time, it starts to get warmer. And then something interesting happens around 0 degrees. This is actually true. It kind of flatlines for a little bit of time. So think you're still adding heat. Heat is constant through all this. You're adding a constant amount of heat to the ice cube. The temperature doesn't change, but time passes and heat gets added. That's kind of weird, right? And then after 0 degrees, it starts increasing again until it gets to about 100. And then at 100, again, it kind of flatlines for a period of time. So heat's still being added, but the temperature isn't changing for a long period of time. And then after a longer period of time, the temperature of the water starts to increase again. So you might have thought that if you look at just a graph of water over time, it would just be a straight line. And you might be wondering, why are there these flat lines here in between? Well, I said earlier, what do we know about 0 and 100 degrees Celsius? What you might know is that 0 degrees Celsius is the melting point of water, and 100 degrees Celsius is the boiling point of water. So during these flatline periods, what we're actually seeing is that energy is required to change solid water into liquid water. So we'll see that the melting point is kind of right here on that first flat line, and evaporation is kind of that second flat line. So the energy is going in to actually changing a solid to a liquid, or ice to water. Or at 100, it's taking that energy and changing liquid water to gaseous water. So that actually takes energy, which is kind of interesting. We might not think about that. But then remember, if I go back a little bit here, remember that solids move slowly, particles move fast, and gases move very, very fast. So you have to kind of give those particles actual energy to get them to move and kind of change from a solid to a liquid to a gas. So anyways, here's where we were, melting, evaporating. So yeah, in this first kind of line, diagonal line, we're looking at ice. Second diagonal line, we're looking at water. And the third line, we're looking at steam. So I put a little S, L, and G next to them for solid, liquid, and gas. I don't know if you noticed that. That's how chemists do it. So yeah, this is the phase change graph of water. Why does this happen? We said that it takes time and energy to heat up an object, and the energy is used to move particles further away from each other. So kind of that energy is taking it to actually change it from a solid to a liquid, which is kind of interesting. So here's kind of what's happening with the particles. Here's a little animation I got for you. These are all particles of of ice right now. And these particles don't really just stay still. They're kind of vibrating. It's hard in PowerPoint to show a circle vibrating, so instead I just have them flashing. So be prepared. Here they are, flashing. So these are just particles normally as is, but then what's happening is we're adding heat to them, right? So I got these little 3 fire emojis down at the bottom. As we add heat to these vibrating particles, what's going to happen is they're going to start to spread out from each other. And this isn't 100% true. I mean, like these particles will kind of be moving from place to place. But the idea is as we create more space, now we're able to change things like volume. Instead of it being fixed, it can kind of be a little bit more variable. Or we're able to change things like, that's shape. Or we're able to change things like volume, where we can kind of like compress them a little bit closer to each other because there's so much empty space in between. So hopefully getting a chance to look at this phase change graph and getting a chance to see these particles, hopefully that tells you a little bit about solids and liquids and gases and the changes between solids and liquids and gases. Things you need to know for today, you're going to need to know what each of the 6 phase changes are. And then the other thing you're going to need to know is, from this other slide, this guy right here, that solids have a fixed shape and a fixed volume, and that they move slowly. Liquids have no fixed shape, a fixed volume, and particles move. And gases have no fixed shape and no fixed volume, and their particles move fast. Those takeaways, in addition to the phase changes, are what you're going to want to know for today. Thanks for paying attention, guys. Thanks for listening. Have a great rest of your day.